midterm exam number 2 was 2 points lower than midterm exam number 1. Let me share my screen here, and you will see, or we will all see the statistics. We will all see the statistics on where we are as far as um, midterm exam number 2. These are the numbers, just an overview of where things are with respect to, the with respect to number 1 midterm exam number 1. The average score was 87%. The highest was 100%, lowest was 40%. Please, the average time taken to complete the exam was around 1 hour, 5 minutes, which this tells me that the time allocation was enough for you to, you didn't run out of time. But this was 2 points lower than midterm exam number 1. Please, I recommend that use the sensitization, complete the homework assignment before taking the quiz, and before taking the exam, you should complete the homework assignment, the quiz, and please do not use only the homework assignment as a benchmark. Do some remedial work, extra work on the chapters and the suggested reading sections. Do not just rely on the PowerPoint lecture. Do not only rely on the lecture recording. That one may not really help you much study extensively. So today I want to get started with chapter 7, periodic trends, periodic properties of element on the periodic table. All right, periodic trend. All right, periodic trend and periodic properties of elements. So today we will start a new chapter, chapter 7. And I know this chapter, periodic table, it's not something new to you. You have used a couple of times. You'll see over and over again. Periodic table of elements. It's just the list of element shown. All right, let's see if it's going to work. No, this is not what I want. I want to share my screen with my whiteboard. This will help now. All right, this is what I wanted, so that you can see the PowerPoint slide at the same time, my whiteboard, in case I need to show you something. All right, let's see here, section 5, 7.1, development of the periodic table. You know what periodic table, this table here is familiar to you. All right, we will start off with how did we end up with this table right here. In the early days of the chemistry development of chemistry in 1600 or 16th, 17th century, there were a handful of elements at that time. What I mean by known elements, during the coinage, there were just few elements known at that time. Gold was one of them, all right, silver. And at that time, it wasn't really a big deal memorizing the names, but over time, a lot of, or a couple of elements were discovered, and chemists were faced with the challenge of, classifying or grouping the elements. That how do we classify all these elements? And remember, there were more elements being discovered. Even as we speak right now, more elements are being added onto the periodic table. Right now, we have about 118 or so element on the periodic table. And down the line, we may have 200 elements, we may have 250, who knows, because of ongoing discoveries of element. So there are a lot of scientists working on organizing the periodic table, organizing the elements. And basically what they were basing on were two things. Periodic tables was organized based on the physical, all right, physical and chemical what? Chemical properties of those known elements at the time. They were basing on that. I don't know why my whiteboard, you should be able to see. Let me see something here real quick. Hopefully it's gonna work. Yes. So this table here, how we ended up with these scientists who are basing on the physical and chemical properties of elements, that the density, the atomic mass, and chemical reactivity, that this one react the same way as this. And there are two, you'll see quite often two gentlemen being mentioned. Dmitry Mendeleev was a Russian chemist, is credited with the organizing the modern periodic table the way it is. There was a German scientist also who came up with the same, almost at the same time as Dmitry, in organizing the modern periodic table, but you will not see Lotus being mentioned because of one reason. Mendeleev was able to predict yet undiscovered element at that time, and therefore he gets the credit for developing the modern periodic table the way it is, even though he was not using the atomic mass the way we know. He was based, or his periodic table was based on the mass of the oxide of the element. What he did is, for example, took lithium, react with what? With oxygen to end up with lithium oxide, and then he weighed, then put it this way. He did the same thing with sodium, for example, react with what? React with oxygen, ended up with sodium oxide, and then weigh, and then organize the table the way it is. His approach was in a way more, all right, he was close to the way the modern periodic table is arranged according to atomic mass. We will talk about that later, all right? So Dimitri is credited for organizing the periodic table. What you see on the PowerPoint slide is just, the color coding based on the years those elements were discovered. I will not ask you, in which year was cadmium or silver was discovered, but just this is an overview of how the element have been discovered. If you see 1965, it means still going on. In 2012, there was an element which was added onto the periodic table. If you go to IUPAC page, you may see an updated version of the periodic table. This table, table 7.1, highlight the reason why Mendeleev is given credit for organizing the modern periodic table. He was able to predict, all right? He was able to predict the germanium on the periodic table. This was missing at that time, germanium and gallium, all right? The elements below these two, aluminum and silicon, all right? They were missing at that time, and Mendeleev predicted that when those elements will be discovered, all right, this is what he predicted. But when those elements were discovered, you can look at how close he was in terms of predicting the atomic weight, all right? The two atomic weight, of germanium. This is for germanium. If you look at this germanium, the atomic weight 72.59. This is the actual. This is what he predicted. This is the density. This is the actual. All these, if you look, they are almost similar. Therefore, the scientific community actually gave him the credit. The German guy, all right, the German guy here, Lothar Meyer, also arrived at the same conclusion almost the same time, but Mendeleev is given credit because of this prediction that he was able to predict those yet undiscovered elements, and two only elements, germanium and gallium, with their properties. Germanium, all right, and gallium were the elements he predicted. Now, recall, all right, up to this point, remember Mendeleev was based, or he organized his table based on atomic masses, not atomic number. There was English chemists who organized now the modern periodic table based on the atomic number. This atomic number is the same as the position of the element on the periodic table. Henry Moseley here, all right, at this time, much earlier, about 35 years earlier, Ernest Rutherford had demonstrated the use of alpha particles, positively charged particles, bombarding the nucleus. Remember the Rutherford model of an atom? I was able to bombard the nucleus. Likewise, mostly what he did was he used high energetic electrons to bombard the nucleus of each element. And every time an X-ray of characteristic wavelength was emitted from the nucleus of all the elements known at that time. So he assigned those energetic X-ray emitted by the nucleus of each element, he assigned a whole number which we now call the atomic number. From this slide, take home point here is the atomic number was assigned by Henry Moseley. All right. He developed the concept of atomic number doing the experiment of which the number of protons was considered as the basis for the periodic property of elements. So you know now that the table you see here, number 1, number 2, number 3, number 4, is what we call atomic number for each element. And you know what they are on the periodic table. I will not ask you to, or no one will ask you to memorize those numbers, but you should be able to identify the atomic number, which is different from the atomic mass or atomic weight of each element. Now, the term periodicity is when those elements now are arranged from left to right on the periodic table, there are some recurring patterns in terms of chemical reactivity and physical properties. We call this repeating pattern periodicity. When elements on the periodic table are arranged according to atomic number, there are some recurring periodic properties. When we organize according to atomic number, not atomic mass. What we'll be talking about or looking at the periodic trend in chapter 7. In chapter 7, we will look at the atomic sizes of neutral atoms and the ions. Remember, ions are charged particles, ions. These are charged particles, all right? And the size of ions will the size of ions will vary in a certain way on the periodic table. This could be, if I have here atom, this is just a neutral atom, but ion, the sodium ion in this case, ion Na positive, Na positive is what we call the ion. And there is a repeating pattern here, which there's a repeating pattern which will be changing. Ionization energy, we'll also look at the trend on ionization energy. Ionization energy is simply the minimum amount of energy required to remove an electron from a neutral atom in its gaseous state. There is a pattern in which this ionization energy changes on the periodic table. When an electron is added onto a neutral atom, energy is given off. We'll also look at the trend on the periodic table. And just wrap up the chapter on looking at specific groups on the periodic table. You know what groups are, the vertical columns, you know, group 1A, alkali, group 2A, metals, alkaline earth metals, group 3A, group 4A, 5A, 6A, group 7A, halogens, and group 8A, noble gas. Those are the groups we will look at. We will look at in chapter 7. These are the trends we will look at. Now, but first we will look at what we call the effective nuclear charge. All right, this is a fundamental property which also follows some trend on the periodic table. It follows some periodic trend on the table. Let me see if my I need to charge my slide here. So the effective nuclear charge is simply the charge experienced by an electron or electrons in the outermost shell or valence electrons or electrons. For example, here, if I look at this is an illustration of sodium atom based on the number of protons. And the valence shell here, valence shell contain what we call valence electron. For sodium, there is only one what? There is only one electron. And of course, for group 1, you know, all of them, they have one valence electron. In the nucleus, we have 11 protons. And of course, there are neutrons in the nucleus. But here, let's look at the electrons and the protons. As far as the effective nuclear charge, we are basing on the net positive. It is the net positive charge experienced by this valence electron in sodium. If it, of course, other elements with more than one valence electron, we will be referring to the valence electrons, that each valence electron will experience a net positive charge we call effective nuclear charge, C effective, all right? See the notation for that. And for these depend on the attraction. Now on these inner electrons in the nucleus, they repel each other because of negative Y repulsion, because they repel one another. But if you look at these outermost electrons, it cannot, you know, positive and negative do attract. But because of electrons moving around the nucleus, this valence electron is shielded. To some extent, there is what we call shielding, that it is shielded. There is shielding of electron that it cannot see the nucleus, or in other words, the force of attraction between the proton in the nucleus and the outermost electron in the sodium will be shielded by the inner electron. So I want you to understand that there are two types of electron here now. And for any other atom, not only sodium, we have what we call the inner electron, or the core. Core electrons are the 10 electrons being referred to here. 10 electrons. But the valence electrons now is what we are basing on what? On calculating the C effective forces of electron experience depend on those two effective nuclear charge. C effective here, this is the net positive. How do we calculate? And this is for what? This is for all the valence electrons. When you look at the C effective, it is the overall net positive. This term right here is defined as the net positive charge experienced by valence electron. And there is a way to calculate the positive net charge. I will not go into the Slater rule. There's what we call the Slater rule on how to calculate that. I want us only to look at a general way of calculating the C effective, which is the positive charge. C stands for the atomic number. You know what atomic number is. We just looked at that. It's the position of an element on the periodic table. Z stands for the atomic number of the element in question, all right? And S is the number of core electrons. S is the screening constant, usually close to the number of inner electrons. What I mean by inner electrons is the core electrons. Maybe before we look at an example, all right, or maybe you can look at the example on this, and then I'll come back to this table. I'll come back to that table. Maybe we use this to calculate the C effective. Let me see if my whiteboard is working now. I'm just gonna show you how the C effective is calculated for sodium. For sodium, how do we calculate the C effective? Remember, C effective is given by, it's retorting back to that, is given by minus S, where S is the atomic number. In this case, I'm gonna show you in a minute.
If you're writing anything on the whiteboard, we can't see it.
Yeah, so let's see, you can see that. All right, let's see that. This is what I was showing you for sodium. All right, let me just show you the whiteboard. Okay. Can you see now? Can you see now?
Yes, sir, we can see it now. Thank you.
All right. Oh, it's going back again. All right. Let me quit and start over again, because I don't want to go back and forth. Same thing. I'm gonna stop sharing and just load one more time the whiteboard. I'm just going to load my whiteboard so that we don't go back and forth again. Hopefully it's gonna work. All right, let's see. So hopefully if this doesn't work, and then I'll just have to use my, I will use the mouse, and then we continue with the lecture. If this doesn't work, and then we'll just have to continue with the, yeah, it doesn't work. Might go back again. I don't know if it's gonna go back. Yes, it's going back again. So anyway, this is what I was saying as far as the C effective, we can use the equation, all right? You can use the equation we looked at earlier on, C, all right? The equation for calculating the C effective. C effective is given by the atomic number for the element in question, which is what? Which is for this sodium atom. For sodium atom, atomic number 11, all right? Atomic number 11 minus the core electrons, minus the core electrons, which in this case, core electron is the number of electrons, excluding the valence electron. Valence electron for sodium is 1. And if we have 11 electrons, the core electron in this case is what? Is 10. So 11 minus what? 11 minus 10 for the core electron. The inner electrons here are the core electron for sodium. We have what? We have 10 core electron, which is positive 1. I know it coincides with the valence or the oxidation number, if you recall from chapter 4, oxidation number, all right, it is totally different from oxidation number. Use the equation given here. If you asked to find the C effective for an atom of a particular element, you'll have just to look atomic number, which is the position on the periodic table, minus the core electron. This one you may want to write the electron configuration, or if you can determine the valence electrons, you subtract the core electrons to get the C effective. What it turns out that for the first 18 elements on the periodic table, if you look at the elements on the periodic table, the first 18 or so, lithium all the way to argon, there is a trend on the C effective that as the atomic number increase, remember the black one here, atomic number, it follows the same pattern for the C effective force calculated with the advanced method. We will see that there is a general increase, all right, across the what? Across the periodic table, across the periodic table. As you go down, there is a slight what? There is a slight, increase. And the point here is, as far as the C effective, what is the trend on the periodic table? There is a slight increase as you go across the table. That's what thing I want you to know as far as that pattern is concerned. How does it change as we move from left to right on the periodic table? As you go down, what is the trend on the C effective? What is the trend on the C effective? Remember the 4 patterns? We have to look at that C effective first. Now, before we look at the atomic trend on the atomic sizes on the periodic table, it's good to understand the definition of atomic radius versus the bonding atomic radius. When 2 atoms, all right, collide, before they bounce or before they form a bond, or non-bonding atom or van der Waals is the shortest. This is just the non-bonding atomic radius from the nucleus to the outermost shell where there is an electron. Divine that. The point here is just defining the radius and how does the trend changes? How does the trend changes? As you move from left to right on the periodic table, all right, left or right on the periodic table, you will see that as you go across the periodic table, the atomic radius decreases. As you go from left to right, the atomic radius decreases. As you go down the periodic table for a particular group, the atomic radius increases. The atomic radius increases. The reason why this may be, I wish I could just have my whiteboard to illustrate the reason why you see this pattern. Is because of when you go across the periodic table, the nuclear charge keeps on increasing. For example, lithium, beryllium, as you go across, the atomic number increase, and of course the number of proton increase, but you are adding electron to the same to the same shell, and therefore the force of attraction between the proton in the nucleus and the electron outside the nucleus keep on increasing. And when it increases, when the force of attraction increases, it tends to shrink the atom, making the atom small and small as you go from left to right. Because of this C effective, remember the positive charge, because you are increasing the nuclear charge, number of protons, number of electrons, and if you have large number of electron in the nucleus, proton in the nucleus and electron outside, they tend to shrink the atoms. Likewise, as you go down, here, increasing from top to, because the N increase, what this means is the number of what? The principal energy level increase, the principal energy level increase. That means as you go down the groove, the number of shells keeps on increasing, and that will change the way the radius keeps on changing, all right? I thought this might work, but still. It's not giving me that. I hope it's not gonna go back. Let's see. So as you go down, as you go across, look, it's like you are adding electron to the same shell. You are adding electron to the same shell, which means the number of electrons, all right? The number of electrons keep on adding to the same shell. But when you are going down the periodic table, the number of shells keeps on increasing. So there will be so many shells as you go across or as you go down the periodic table. This explains this trend. Now, apart from knowing the general trend on the atomic radius, that it is increasing, it is decreasing as you go across, you need to be able to organize also a list of elements. In the exam or in the quiz, you may be given list of elements as, for example, boron, boron, carbon, nitrogen, and oxygen, and you are asked to arrange according to increase in atomic radius. You should know their position on the periodic table. Without memorizing the numbers given here. You may be given a list and say, according to decrease in atomic radius, you should also see the pattern, how it is changing. So that's the general trend on the atomic radius. This is an example on, you may see in the exam, which part of the periodic table, top or bottom, left or right, has the element with the largest atoms. Bottom and left, bottom and right, top and left, top and what? Right? Use the chat window. Let's see, somebody, yes, bottom left. Yes, thank you, Catherine. Bottom left, Lauren, thank you. That is good. Yes, the bottom left, because as we saw from the trend, all right? As we saw from the trend here is just a summary of, if you look at without going by the numbers given, you'll see that on this region, this is assumed to be the periodic table. Same thing, that it's bottom left, general trend on atomic radius. Now, ions can be positive or negative. Cations are positively charged, anions are negatively charged. Ions are formed when a neutral atom loses one or more of its valence electrons, and metals tend to lose, of course, you know that. And non-metals tend to gain electrons to what? To achieve the noble gas electron configuration. So with that, there is a pattern here on the trend on the ions. If you look at the cations versus the neutral atoms, cations tend to be smaller than what? Than the neutral atom. This is sodium neutral atom. If you look at the cation, likewise for magnesium, likewise for potassium, always for cations, for neutral atoms, they are cations are smaller, whereas anions are bigger than what? They are bigger than their parent atoms. They tend to be bigger. So here is just what you need to remember in terms of the trend on what? On the trend on the pattern, the size of cations, the size of what? The size of the ion in comparison with the neutral atoms. The pattern you see here depends on the nuclear charge. Of course, you know what nuclear charge is. That's the number of protons, of electrons, and so forth. You may see, all right, you may see a mixture of cations and anions. Still, you'll have to combine the general trend in the atoms compared to the general trend in the radius of the neutral atoms compared to anions, and make a conclusion how it is changing. So from the picture here, cations positively charged, cations are always smaller than their parent atom because we are removing electrons. Think of, for example, sodium, we remove the 3s electron. We remove the 3s electrons, it's just gonna go away, making the sodium cation small. Now, anions, which are, you see here, anions are shaded blue. They are always larger than their parent atoms because we are adding electrons. Additional electrons make the anions, which are negatively charged, larger than what? Larger than their parent atoms. So that's what you need to take home from this slide, that how does the trend on cations compared to parent atom, how does the anions compared to their parent atom changes on the periodic table, There is a time here which you need to recall. This was in Introduction to Chemistry. If you recall, isoelectronic. What does isoelectronic means? Isoelectronic series are, these are series of elements. It could also include ions with exact same number of electrons, all right? And isoelectronic series are ions have the same number of electrons. They may also have the same electron configuration. And the ionic charges or ionic size for isoelectronic increase with increase nuclear charge. The 3 or 1, 2, 3, 4, 5. If you look at these, ions, the first 2 cations, the last 3 cations, these are anions, negatively charged. We call these isoelectronic ions because they do have what? They do have the same number of electrons. If someone asks you to write electron configuration for all these, they look exactly the same. And the pattern here is ionic sizes for isoelectronic series decreases with increase in the nuclear charge. I would say, nuclear charge here is just basically the atomic number. Nuclear charge is the number of protons, which is basically what? The number of neutrons. We cannot change the nuclear charge. You cannot rip the nucleus and remove the proton. We cannot do that. The only thing you see changing here is when we lose an electron from the outermost shell, the properties of an element changes. So here, the nuclear charge is the number of protons. If you remember, atomic number 8 is oxygen, atomic number 9 is fluorine, atomic number 11 is what? Is sodium, atomic number 12 is magnesium, and atomic number 13 is aluminum. So if I know the atomic number, if you are asked how is the pattern, you may not be given also these numbers without necessarily using the numbers given here to do what? To make a conclusion that the ionic sizes decreases with increase in atomic. I can use just the atomic number and say it is decreasing with increase in atomic number. All right, and because of what I just said earlier on, that when you increase the nuclear charge, which is the number of protons in the nucleus, it tends to pull the electrons towards the nucleus, therefore decreasing the size of it's an isoelectronic series, but generally for an ion. So you need to remember the pattern in change in the sizes of isoelectronic series. That means they have the same number of electrons, they have the same number of electron configuration, that it is decreasing with increase in atomic number or nuclear charge. This is the decrease in the nuclear charge. So I may give you isoelectronic and say arrange according to increase in ionic radius, arrange according to decrease in ionic radius, or which one of the following will have the largest ionic radius, the smallest ionic radius. No matter what, still you use the same conclusion. Use the same conclusion. How do cations of the same charge change in radius as you move down a column on the periodic table? Remember, they have the same as you move down. They have the same charge. As you move down a column, is it increasing? Is it getting smaller? Minimum change? Larger change? Remember, you are moving down. We looked at it earlier on here, all right, as you go down. They have the same charge right here. There is a slight change in, though it is not apparent, but there is a slight change. So you can use elimination method. Is just a general understanding. They have the same ionic charge. We are looking at the what? They are looking at the same charge, whether it is +3 or +2. As you go down, there is a small change. You see 1.21, 1.22. As you go down the column on the periodic table, it's not a large, minimal change. So there's a change, but it's very minimal. All right, let's see ionization energy. Ionization energy.
So what was the answer to that one?
This one, there is a minimal change for ionization, or no, for the radius.
Okay.
Yeah. Minimal change for that. Let's move on to 7.4, ionization energy. This is defined as, or I here you see that I for ionization energy, it is the minimum amount of energy required to remove an electron. Not electrons, you cannot remove 2 electrons at the same time. It's to remove an electron, underline the word electron here, from the gaseous state, all right? From the ground state of a gaseous atom or ion. So that means you will have removed one, and then you go back and remove another one. That means you are dealing with an ion here. You will see fast ionization energy. You'll see fast ionization energy like that. For one with a subscript, that means fast ionization energy. Second ionization energy, and then third ionization energy, and so forth. Even fourth ionization energy. That means you remove depending on how many electrons you are removing. If you are removing the first electron from a neutral atom, we call that fast ionization energy. So when you see fast ionization energy, that means when removing the first electron. When you go to remove, or when you remove the second electron from the ion now, we call that second ionization energy. Removing the third electron, that is the fourth ionization energy. So remember, there is that sequence, there is that pattern. Second ionization energy is required to remove the second electron, third, and so forth. And note here, the higher the ionization energy, the more difficult it is to remove an electron. Picture this. If we have, let's use sodium, for example, which is atomic number 11. It has 11 electron, 11 proton in the nucleus. It is neutral. So if we remove the first electron, that means we are remaining with 11 proton in the nucleus, attracting 10 electrons. So we have more power from the nucleus, pulling the 10 electron. And if you could remove the 10th, we took away from the first ionization energy. To remove the 10 electron from now sodium ion, which is now the second ionization energy, it is more difficult because the more positive or the more nuclear charge we have, the more difficult it is to remove an electron from an already ionized species. It is a cation. If it is a cation, so remember, we are all ending with what? Cations, because removing an electron, we end up with a positive species, with a positive species. There's a pattern here, which, there is a table. I think I need to close this. There is a table which here, table 7.2 for sodium, magnesium, aluminum, silicon, phosphorus, all the way to argon here. What you see here is element, and then first ionization energy, second ionization energy, third ionization energy, fourth ionization energy, fifth, sixth, and seventh ionization energy. To remove, that means to remove what? To remove the seventh electron. We only have one, what? We only have one electron, or one valence electron for sodium, and the amount of energy required in kilojoules to remove that one electron, the first ionization energy, is 496 kilojoules. What you see here as shaded or missing, these are the inner, like, we are removed the valence electrons. So here is represent the valence electrons. Here are the long electron, the core electron. For example, let's say aluminum is number 13. It has 3 valence electrons, right? 3 valence electrons. So first ionization energy, 578. We are remove 1 electron. Then we remove the second electron from already positive aluminum. This is second ionization energy. And the last valence electron, is more difficult to remove that. This keeps on increasing. Once we are done with the 3 valence electron for aluminum, we are now dealing with what? With the core. We are now getting into the core electrons, and these are the amount required to remove that. This is not gonna get into that. So here are just the pattern on the amount of energy required to remove successive electrons for each element. Which there is a pattern here that the ionization energy keeps on increasing based on the number of valence electrons being removed for each element. It takes a great deal more energy to remove an next electron. That means the core electron from an already ionized species, an already ionized species. Let's see here, is the conclusion on ionization energy. When you see this subscript right here, it means fast ionization energy, to remove the fast valence electron. And generally, there is a periodic trend in the fast ionization energy, I1. Generally, it increases across the periodic table. So as you go across the periodic table, it increases from left to right. But when you're moving from right to left, it decreases. You got to know where you're moving to. Now, fast ionization energy generally decreases down the group, of course, because of as you go down a group, the number of shells keeps on increasing and there is more shielding. That outermost shell, as the number of shells increases, you go down a group, the outermost electrons do not feel that C effective, do not feel that force of attraction by the protons in the nucleus. There is the shielding of that outer, and therefore it is very easy to remove that one electron because of the shielding effect. Therefore, it's generally do what? It decreases down a group. So these are the general trends you need to know. And then, of course, if you are given a list of elements, maybe in one group, and you are asked to arrange according to either decrease or increase in the fast ionization energy, you can use this. Now, for these are for SN, but for D block, for SNP, you know what SNP, what this means is when you write the electron configuration, the last electron ends up either in S or either in P sublevel. We call those SN block element. If you write the electron configuration, if you look at the electron configuration for elements on the periodic table, the last electron, if it ends up in S or P, we call those P block elements. If it ends up in D, we call those D block elements. If it ends up in F, we call those F block elements. So for S and P block elements, they show larger range of values for fast ionization energy. Now, D block generally increases slowly, but it's not significant. It's not significant. There's some variation. I don't know, I don't want you to memorize the numbers you see here for each element. These are the fast ionization energies. If you look at hydrogen, it is so difficult. 13. It's very difficult to remove electrons. The smaller the size of an atom, the more difficult it is to do what? To remove the electron, because the electrons are closer to the nucleus. They feel that impact from the what? From the protons, and therefore it is very difficult to remove that electron. Therefore, it's so hard. Now, generally, as you go down a group, all right, this is what we looked earlier on, it's decreasing the ionization energy. Decrease. And as we go across, it increase or it decrease. So be careful on how the questions are framed. You may memorize this table, but the question in the exam will be, as you move from right to left, how is the trend on ionization energy change? And somebody say, I remember it was increasing. No, when you go this way, how does it change? when you go down, it's not increasing as you go down, it decreases as you go down. But here the other is, using as you go up the periodic table. So I'll be careful on when you're reading the questions so that you understand clearly how to respond to that. Now, there are some irregularities in the general trend. The trend is not followed when valence electron in the next element are added. In the next element, if it enters a new sub-level, higher energy level, then it changes. If the fast ionization energy to pair in an orbital of the sub-level electron repulsion, lower the energy, So if you look at the p electrons in nitrogen, we don't show here the core electrons because it's the same. For oxygen, we start pairing them up, writing the electron configuration. Electrons are negatively charged and they tend to repel one another. Therefore, it lowers the energy. So this one, if it is paired up here, remember electrons are what? Electrons are negatively charged and they tend to repel. So if you are removing something which is being kicked out, it's very easy to remove, right? But here, there's no pairing. So we will need more energy here to remove any of these electrons. But to remove here, it will be much easier because of repulsion. So to make a conclusion on which one will have low fast ionization energy, you may want to write the orbital filling diagram electron configuration for an element in question or element in question to really see this repulsion of electrons in an orbital within the sub-label. This is P sub-label, this is the orbital, this is the orbital, this is the orbital in P sub-label for nitrogen and oxygen. And the point here is electrons repulsion lowers the fast ionization energy, And I think there was a question here on oxygen and nitrogen that why is it easier to remove a 2p electron from an oxygen atom than to remove an electron from 2p sublevel in nitrogen? Let me see how you respond to that. Using the chat window, you can use that. Let's see. How will you look at that? What is this is the question. That is the question. Why is it easier? Remember what we said earlier on about, I just explained that. Let's see, somebody. Yes, Lawrence, C, it's correct. You cut that. Let's see back here. I want to show you why that is the case. We just from here, if we go back here, the first electron to pair in one orbital of sublevel, electron repulsion lowers the energy. So here there is the repulsion of electrons. These two, and to remove this, it will be much easier. If you look at this, decrease electron, electron. Why is it decreasing electron, electron? It's not decreasing. In fact, the repulsion is increasing. Therefore, A is wrong. No, just nothing. It is C because of increased electron, electron repulsion. Therefore, it is much easier to do what? To remove that electron in the oxygen than in the nitrogen because of electron, electron repulsion. Electrons tend to repel one another, and therefore, it is much easier to do it, to remove an electron. So the only way you can look at that is if you write the orbital filling diagram using the up and down arrow to see the electron, you will be able to see paired electrons. In chapter, down the line, I believe chapter 8, the orbital filling diagram will also, I think 9, will also be handy in terms of figuring out some other stuff I'll talk when we get there. So you got to be rounded with up and down arrow, how you write down the electron configuration. Having said that, if you know how to write the electron configuration of a neutral atom, one has to remember what I write last time and then use the arrows to give you the how electron occupy the sublabel according to increase in energy shown here. If you know how to reproduce that to generate that diagram, then you should be able to write electron configuration of ions.
We can't see the PowerPoint anymore.
Thank you. Let me just show you that. I thought I stepped out for a minute when I was looking at that. So this is what I was talking about, that if you know, all right, if you know how to write the electron configuration, you can see now, right? Can you see the screen?
Yeah, we can see it now.
Yes, thank you. So this is what I was saying, that go back again. Remember the diagram I generated last time on how to write the electron configuration. It's very common that I draw the diagonal to help me understand or arrange the sublabels, how electrons are arranged in an atom according to increase in energy. Somebody may think that, okay, we are done, we have to do with the 4, and then we go with the 5s, and then we go with the 6. There is an overlap as the n value increase, and that diagram will help you out in writing electron configuration and writing electron configuration for ions. And remember, ions can be cations, it can be anions, and it is very simple. If you know what, or if you know what the overall charge means for cation, if you know what the overall charge on the anion means, and then writing the electron configuration will be easier. For cations, the overall charge indicates how many electrons you are less by. If it is Mg positive 2, that means you are less by 2 electrons. So you write the way you write what? The regular electron configuration, but you omit 2 electrons. For example, here, why are we saying, we know generally lithium has 3 electrons. It is 1 as what? You'll write, let me just annotate this. You may want to see that 1 for lithium is given by 1s2 and 2s1, all right, 2s1 for atomic number 3. But for lithium, we are cation positive, we are less by 1 electron, and therefore this one will go, and therefore you see this is the electron configuration for lithium cation, I'll do the same thing for any cation given on the periodic table. If it is sodium, all right, if it is sodium, and then you have to write the electron configuration -1. Now, when it comes to d block elements, that is, you know where the D are, all right, you lose the 4s fast before what? Before, let's say here, if I didn't have this, let's just, for a minute, we don't have that, and then you'll have expected here to have 4s2, right? 4s2 here. You may think that I'm gonna remove one electron from here, or 2 electrons, and I think there was some typo here. This should have been +2. We remove 2 electrons, ion 2 and ion 3. You know, they are ion 2 and ion 3. So we'll remove the 2 electrons. So I'll just have to clear that. All right, all drawings. And if this is +2, the 4s is gone. And then we come and now remove 1 here for F3. If it was F3 in this case, all right, if it is F3, let's say 3 here, and then I'll remove here and make it D5. I'll make it D5 because the 4s, 2 electrons are gone, and the 1 electron from the D is gone. That is how the electrons are, or electron configuration for cations in diplo elements, that the 4s electrons are removed fast, and then you go now to the 3d sublevels, remove how many you have, depending on the overall charge for the elements. For anions, you just have to add how many electrons you have added. Nitrogen, for example, just here, nitrogen with an overall charge of -3, nitrite, all right? This is nitrite. It's gonna be 1s2, 2s what? 2s2, and 2p what? 2p what? You are adding what? Nitrogen is number 7. So instead of adding, for generally 7 for battery there, NP3 nitrite, you have add 1s2, 2s2, 2p what? 6. Nitrogen is number 7 on the periodic table. All right. Let's see how you end up with that. If I have here I wanted to say nitrogen is nitrogen here is number 7. So if we are 1s2, 2s2, 3p3, and extra electrons from the negative means we have excess 3 electrons for nitrogen, 3 electrons. So it is built up. Electron configuration for ion is just an extension of writing the electron. In this case, it's just only cations, positive or negative. You know, see, of course, polyatomic ions. Any question? Let's move on to 7.5, electron affinity. Electron affinity is the energy given off or accompanied by addition of electron into a neutral gaseous atom. When an electron or electrons are added, energy is given off. They are generally exothermic. Energies are given off when electrons are added onto neutral atom. We call this electron. And there is a what? There is a pattern as well on the periodic table. This is the general trend that as you go across, it decreases. You know, from Mars, this means greater. If I look at generally, even though it's not well defined, but we can see that no much change in a group, like, you know, within a group, there's no much change, zero, as you go down. Generally increases, even though you may say that I don't see there is some discrepancy, but generally it keeps on as you go. But as you go down, there is no much change in the trend. And all of them, they are negative. And understand that negative means it's exothermic, it's given off. The amount of energy released. So that's one trend I want you to also commit to your memory, understand how it's changing on the periodic table. The last bit of chapter 7 is looking at the specific groups on the element on the periodic table and see their chemical reactivity. If you look at the periodic table, they have some color coding which separates or which indicates the metal territory, the metalloids, and the non-metals. Hydrogen is on this side, even though it is a non-metal because it behaves as a metal in one case, and also it got some properties for non-metals. Generally, if you look at here, if we start from the left of the periodic table, going across, we are on the metal territory. We are in the semi-metals. These are semi-metals, and then the non-metals. So even though what is happening here, even though we are in the metal territory, the metallic character decreases. I want you to understand what is happening as you go across, the metallic character decreases. But if you are going from right to left, the metallic character increases. Even though I may be in the metal territory, the metallic character is increasing. So on this side of the periodic table, it's more metallic. On this side of the periodic, it's less metallic. And if you go down, the metallic character also do what? It increases. So I can say between potassium and rubidium, this is rubidium, this is cesium number 55 and francium number 87. Francium is the most metallic, even though it's radioactive. Cesium is more, it's less metallic compared to that. So note the general trend that apart from what we learned earlier on, that this is non-metal, this is a metalloid, this is non-metal, we can also talk about the metallic character. I can say, based on this conclusion, that chlorine is more metallic, all right, compared to argon, for example, because it's increasing as you go from right to left. We can say phosphorus is more metallic than either silicon or chlorine. Say that the pattern on metallic character. Metalloids, of course, there are properties which goes in between those of metals and non-metals. We will look at that. Apart from that, let's see. These are the properties of metals that they tend to lose their valence electron to form cations. Positive one, positive one, positive one, they are in group one. Group 2, they lose 2 valence electrons. Non-metals tend to gain electrons and they form anions. You see now hydrogen is doing what? It is gaining, they share, actually sharing or gaining when it's forming a metal hydride. Group 8, they don't gain, they don't lose, you don't see anything on them, all right? Take note of special property of hydrogen. It's in this case, it is gaining. In some cases, it's losing to form positive. So here are the transition metals where cations are formed by losing their valence electrons. Having said that, this is just a repetition of prior knowledge on the periodic table. You should have covered this in Introduction to Chemistry Properties of Metals. They are shiny, of course. If I give you a piece of metal and a piece of plastic, you can tell which one is a metal. It's because of the look. Luster is the look that it is shiny. Whereas non-metals, you can say they are dull, all right? They are good conductors of heat and electricity. Thermal conduction, that's conduct heat and electricity. Non-metals, they are poor conductors of heat and electricity. It's opposite of what you just see here. Malleable, that means you can use a hammer to just spread it into a thin sheet of what? Of metal. That means that's what is meant by malleable. Ductile, that means you can pull into thin wires. Ductile. As opposed to this, non-metals are brittle. You cannot use, if you use a hammer, it will shatter. It will shatter because they are brittle. Most metals are solids at room temperature, except mercury. Mercury is liquid at room temperature. Other than that, non-metals, opposite of this is most of them, they are gaseous at room temperature. We have solid, of course. Iodine is solid. Bromine is liquid, even though it's non-metal. You need to know that. And they have low ionization energy. That means it is easier to remove their valence electron, even mostly referring to I1, fast ionization energy. They are very easy to do it. To remove an electron. We say, if you recall from chapter 4, they are easily oxidized. They are easily made to remove to lose electrons, Here is an example of, you can tell that this is a metal, all right, by the look of it. Now, most of the metals exist in form of compound, all right, such as staple sodium chloride, right? It's got sodium in it, it's got chlorine in it, compounds, 2 or more compound elements combines specific ratio to form compound. You know what ionic compounds, all right? Ionic compounds are those compounds formed when a metal combined with a non-metal ionic compound. I don't want to get in details into the metal oxide and how they react to form solids. Let's just look at non-metals. Please remember the properties of metals are 4x6 index card so that you know, all right? So that you know the properties of metals compared to what? Non-metals, which I just explained when I was going through the slides on metals. Know where they are. Non-metals are found on the right side of the periodic table. We looked at that. These are the properties. We have solids, liquid, and gas depending on the element. Solid iodine, molecular iodine is solid at room temperature. Bromine is liquid, it's brown liquid solid. Brown liquid, not solid. Brown liquid is bromine, and most of the non-metals are gases. Nitrogen gas, oxygen gas, all right, and so forth. Chlorine gas, fluorine gas, they are diatomic. They are dull, brittle, they are poor conductors of it. They have high or large negative electron affinity. That means they are highly exothermic. When you add electron in it, they give away a lot of energy, large negative electron affinity, which means a lot of energy is given off when you add an electron to them. All right, this is non-metals. They are those elements, non-metals. They are just non-metals. They do not, most of them, they are gases at room temperature. Except we have solid. Here is just an example of reactivity of metals that they form. Most non-metal oxide are acidic, all right? This is a recap what I want you to know in terms of properties for metals as compared to non-metals. You will see in the exam or in the quiz or homework assignment that which one of the following is metal, which one of the following is a property of a metal, all right? And then either multiple choice will give you one of them which is correct. All right, if it is for non-metals, you will be given that. Do you think sulfur is malleable? That means you need to know, be able to classify sulfur as either metal. This is a property for metals, malleable, ductile. Is for what? Metals. Yes, I don't think so. It is malleable. No. This is wrong. Malleability is a property for metals. No, it is gaseous in elemental form. No, like other non-metals, it is brittle. It's more, sulfur is solid, so I will not say that this is, yes, no, but it is not gaseous. That's what makes it wrong. No, like other non-metals, it is brittle. Sulfur is brittle, so there is a correct answer for this is solid. You need still to read on the properties of metals use elimination method. The correct answer for this question is C. Read on properties of metals. While you are use elimination method for this to determine the correct answer. Now, metalloids are semi-metals. They have the properties of metals, or their properties goes in between those of metals and metals. For example, here is, I believe this is silicon. It looks like a metal, but does not conduct electricity. All right. What you see here is silicon. And all right, if you look at that, it looks like a metal, but it does not conduct what? It does not conduct electricity. That is silicon you see on the screen. But the way they are used, you may ask me, why is it then, if it does not conduct electricity, they are used in electronic circuits? They fabricate, they add something else they call dopant. To dope is to add something to improve the properties. It will change dramatically. Mixing this with something else, it will change its conductivity dramatically, and that's why they are fine application in electronic silicon. And that is why you hear of Silicon Valley in California, electronics and IT stuff like that. It's because of maybe they are attributing to the use of silicon in electronics. So here is an example of metalloid, and several of them, when they are in pure form, all right, they are good insulators when they are in pure form. That means when nothing has been added. But if something is added to it, they are good electrical semiconductors used in computer chips. And as I said, they mix with some other stuff to improve or make use of that. Now, because of time, which we have 5 minutes, because of time, I don't want to get started with special groups on the periodic table, which I say this is going to be the last thing we look in 7. We will start from special groups and see their trend on their chemical reactivity. Most of the chemistry you will see has to do with main group elements. That is the A on the periodic table. Group 1A, column 1, alkaline admetals. Chalogens, sometimes they use the term halogens or chalogen for group 6. Group 7 halogens. Halis comes from the word sol forming compounds, and the noble gases, they do not react. We will start from each one of them, and then we summarize chapter 7 and move to 8. I want you to get started with chapter 7 homework. Read chapter 8. We will get started on Thursday with 8. And of course, because of time factor, maybe also this week by Sunday, I will make chapter 7 quiz available so that you can get started right away. Other than that, as SI support facilitator Nick, he posted a survey on SI Canvas page. Please do take that survey and let us know when you are available so that we can assist you as we descend. We have engaged the landing gear as far as the semester is concerned. If there is no more question, the class is dismissed. We will meet again on Thursday. If you have no question, thank you, Andel. Thank you, everybody. I'll see you again on Thursday. Please continue reading chapter 8. All right, we'll get started with 8 on Thursday, and I want you to be on this. I want us all to be on the same page. The class is dismissed. We'll meet on Thursday.